Welcome to Pomodoro Joe for Tuesday, August 8th, 2023. Today we're doing LeetCode problem 33, search in rotated sorted array. This is a medium problem. There is an integer array nums sorted in ascending order with distinct values. Prior to being passed to your function, nums is possibly rotated at an unknown pivot index, k, such that 1 is less than or equal to k, which is less than the length of the nums, such that the resulting array is nums k plus 1, so on and so forth, to nums n minus 1, nums 0, nums 1, so on and so forth, to nums k minus 1, 0 indexed. For example, 0, 1, 2, 4, 5, 6, 7 might be rotated at pivot index 3 and become 4, 5, 6, 7, 0, 1, 2. Given an array nums, after the possible rotation and an integer target, return the index of target if it is in nums, or -1 if it is not in nums. You must write an algorithm with O of log n runtime complexity. And then we have some examples. All right, well, before we get started, we'll do a quick analysis of this. Essentially, we have a sorted array, but it may be rotated, so it's shifted to the left or right and wrapped. So we're given this possibly rotated array and a target value that we're looking for in that array. Now we have to return the index of that target value if it's in the array. If it's not, we return -1. And our algorithm has to run in O log of n runtime. So O log n runtime means that we need to cut our search area in half every step along the way. So if you're not familiar with big O notation, I'll try to leave a link in the description. But essentially, this is an estimation of how fast our algorithm will run. So for example, if our array has n elements in it, and if we just did a linear search, if we just went through the entire array one element at a time looking for our target, then that would be an O of n runtime, because we're going through every one of our n elements looking for our target. Now O log of n means that we have to divide our search area into halves and just choose one half and search that area, and then divide that area in half and choose one half and keep going. So essentially we need to divide our search area in half for every step along the way. And that will give us the O log n runtime complexity we're looking for. Before we get started, let's take a quick look at this example. So we've got, looks like 0, 1, 2, 4, 5, 6, 7, but it's been rotated so that 0 starts at index, what is that, 4? 1, 2, 3, 0, 1, 2, 3, 4, yeah. So my initial approach, or my initial thought, is to use our standard binary search algorithm. We'll split our search area into two halves, then figure out which half our target should be in, then concentrate just on that half and do it again. Split that half into two halves, figure out which half our target should be in, and keep going until we find our target or until we run out of elements and we have to return -1. Now typically with our binary search, because everything's sorted, it's pretty easy. You just split at the midpoint, check to see if your target's greater than or lower than that midpoint, and then you can concentrate your search on one half or the other. Now in this case, that's going to be harder, because if we split at this midpoint, which is 7, now if our target is less than 7, it could certainly be in the upper half, or it also could be in the lower half. We don't really know. So just knowing that our target is less than our midpoint isn't really going to help us. We need more information. So one other piece of information that we could find is, where is our wrap point? So the wrap point is basically where we are wrapping around again. So I'm going to call this the wrap point, so 7 to 0. We've sort of shifted everything over, and this is where it would wrap around. So if we find our wrap point, if we have a wrap point, we can find that wrap point either in the lower half or the upper half. Now once we know which half our wrap point is in, that half is going to be tricky to deal with, because if the wrap point is, let's say it's in the upper half, that means from the mid up to the wrap point, we don't know where it is. We're not going to actually find the point. We just know that it's somewhere in that upper half. Now once we know that it's there, everything from the midpoint up to that wrap point will be greater, but then it flips and suddenly becomes smaller. So everything from the wrap point plus 1 to the end is smaller. So we have a bunch of high valued elements and we have a bunch of low value elements. So we don't really know where our element, where our target might fit in there. But that also tells us that if our wrap point is in the upper half of our search area, that means the lower half must be just a standard increasing sequence. And if the low half is just a standard increasing sequence, then we can just check to see if our target is between the start and the midpoint, so the lower half. And the same is true for the opposite. If our wrap point is in the lower half, it's hard to get information about whether or not our target is in the lower half, but it's easy to find out whether or not our target is in the upper half just by looking at the bounds to see if our target is somewhere in that increasing sequence. So that's how I'm going to do this. All right, let's put 25 minutes on the Pomodoro timer and we will get started. So this won't necessarily be the cleanest code or the most compact code, but it should do the job and it will explain how we sort of break this down. And then once we figure out this initial solution, we can go through and optimize some of the logic. All right, so this is going to be our standard binary search. If you're not familiar with binary search, check out yesterday's video or check out some of the links in the description. So we'll have a lower index and an upper index. So the lower index, we're going to start at 0. And the upper index is going to be just the length of our nums minus 1. So that's the maximum index. All right, so these lower and upper indices are going to define our search area. Now, initially, we use the entire list as our search area. And during our algorithm, we'll be shifting around our lower and our upper to basically divide our search area in half every step along the way. Okay, so now that we've defined our search area, our initial search area, we can start going through and narrowing our search area. All right, so while our lower index is less than or equal to our upper index, now we're going to be searching smaller and smaller areas. So we want to make sure that our lower and our upper don't cross. All right, first thing I'll check. Let's get the midpoint. So this is the mid index. That's somewhere right in between our lower and our upper. So that's going to be the lower index plus however many elements we have between our upper and our lower divided by 2. So that's upper minus lower. And we'll divide that with an integer divide by 2. So this will give us our midpoint. I'm going to put this here. All right. Next, let's just check. Is this our target? So if the nums at this midpoint is our target, then we're done. All right. If this is our target, we're done, and we can just return this midpoint as our index for our target. Next, this might not be strictly necessary, but it will help us a little bit. If our lower is equal to our upper. So now we don't have any more elements. This is the last element, and we've already checked that it's not the target. At this point, we can return -1. We're done. Next, let's figure out where our wrap point is, because that wrap point will help us figure out if we're going to look at the left or the right or the upper or lower part of our array here. So let's have some wrap. And for now, we'll just set it to none. We don't know where it is. All right, so let's figure out where is this wrap point. Okay, so how do we know where the wrap point is? Well, if the wrap point is in the upper half of our search area, that means the midpoint will actually be greater than the high value or the upper value. So you can imagine, let's see if this is a good example. Yeah, you can imagine if we've shifted our array such that the wrap point is in this upper area, then our midpoint here will be greater than this upper value here. 7 is greater than 2, right? Because at some point we're increasing until we get to our wrap point. And then once we get to the wrap point, we start at the very smallest value in our array. So then it increases until it gets to the end here. And then it wraps around. All right, so if the nums at our midpoint is greater than the nums at our upper value, or upper index, well, now we know that the wrap point is in the upper portion of our search area. So we'll just say wrap. I'm just going to set it equal to 1. Let's just say 1 means upper. So this will tell us if it's in the upper part. Now, it doesn't necessarily mean the opposite is true. If it's not in the upper part, it doesn't have to be in the lower part. We might not have a wrap point. So let's check here. How do we know if the wrap point is in the lower part? Well, again, it's very similar where if the wrap point is lower than our midpoint, that means our nums at the lower part, the nums at our lower index, will be greater than the nums at our midpoint. So if nums at mid, if that is less than the nums at lower, That means we must have the wrap point in the lower half. So we'll call wrap, and I'll just set that equal to -1, meaning the lower half of our search area. Now to make this easier on ourselves, we could do something up here. This is something I like to do. We could just define wrap upper, and we'll define that as 1, and wrap lower, and define that as -1. Then we can just set it here. All right, so now we know where our wrap point is. It's either we don't have one, or it's in the upper, or it's in the lower. So if we don't have any wrap point, that's the easy path. That means this is our standard binary search. So let's do that first. So if we don't have any wrap point, this is standard binary search. So we just check if our target is greater than the nums at this midpoint. That means it must be somewhere in the upper half of our search area. So our lower becomes our mid plus 1. Otherwise, it's in the lower half of our search area, so our upper just becomes mid. Okay, so that's our simple path. Actually, let's write this here. All right, so that's the standard binary search. Next up, let's try the upper half. Okay, so if the wrap is equal to wrap upper, now if the wrap is in the upper portion, the higher portion of our search area, that means that high portion of our search area from the mid to the wrap point will be the greatest values in our array. And then from the wrap point plus 1 to the highest or index, our upper index, those are going to be the lowest values in our array. So our target could be greater than our mid, but less than our lower, and those, anyway, it becomes complicated. So instead of looking at how it would fit into the upper half, let's just look at the lower half. If we know the wrap is in the upper half, then we know the lower half of our search area is just a standard increasing sequence. So we can check if our target is in that sequence. Is it greater than or equal to our lowest value? And is it less than our midpoint value? So let's just check if our target is in the lower half. If it is, we can confine our search to the lower half. If it's not in the lower half, then it must be in the upper half. So let's do that. So our target is greater than or equal to, now we haven't actually checked to see if it's equal to the lower index, so we better do a less than or equal to our nums at the lower index. And the target is less than the nums at the mid index. That means it must be somewhere in our lower half. And if that's the case, then we can lower our upper to the midpoint. Otherwise, we're going to assume it's somewhere in the upper half, so we increase our lower to mid plus 1. Okay, so that takes care of the wrap point being in the upper half. What if the wrap is in the lower half? Very similar thing here. If the wrap is in the lower half, that means the lower half of our search area has some really big values. It also has some really small values. It's going to be hard to determine if our target's in those ranges. It's easier to look at our upper half and determine whether or not our target is in the upper half just by looking at whether or not it's in between our midpoint and our upper index. So, target is greater than nums at mid. Now we don't have to check equal to because we've already checked if it's equal to mid here. And our target is less than or equal to the nums at the high point or the upper index. Well, in that case, our target must be in our upper half, so we'll increase our lower to the mid plus 1. Now, if it's not in the upper half, we'll assume it's in the lower half, so we have to lower our upper down to our midpoint. All right, and finally, if we make it through all of this while loop without ever returning, then we'll return -1 because we didn't find our target index. All right, so I think this should do it. I'm sure I've made some typos, but let's run it and see how we do. And we pass. All right, let's submit this and see if we can pass all the tests. And it does. So we pass. And we do okay. We beat 72% for runtime and 72% for memory. That's not too bad. Now we can jump back here and clean this up a little bit. All right, so I'll get rid of some of these comments. We don't need these. Okay. We could probably do an else here because it can't be in both. So Okay, let's see if that makes it any faster. Let's see. Ooh, that makes it significantly slower. Interesting. All right, let's get rid of that else. Branching is tricky. Sometimes it can cause it to go faster, sometimes it can make it go slower. It's hard to tell. Okay, we could simplify a lot of this logic. I'm not going to go through that because it's a little bit more complicated, but you can do that if you want. Check it out on your own. Go through and try to simplify this logic. All right, last thing I want to do, I guess we can get rid of this wrap upper, wrap lower. We already know that this is 1 and -1, so we can just do this. Now, I don't recommend doing this in production code because no one's going to know what 1 and -1 mean, but for trying to get some speed boost, let's do it here. All right, let's see if this helps us at all. Not really, 77%. Okay, final trick up my sleeve. We can actually compact this. So as you see, we're doing lower plus upper minus lower divided by 2. So this is lower plus a negative. This is lower minus lower divided by 2, which is actually just plus half of a lower. So let's just do this. Yeah, okay, this is confusing, but it does work. That might save us a little bit more time. Doesn't. Man, struggling to get any gains on this one. All right. Last thing we could try. I'm not totally convinced that this is going to work. We could do mid, upper, mid -1. Let's try it. Looks like it works, but I don't know. All right, that does work, but it, man, takes us down even further. I am struggling to make any gains on this guy. All right, let's go all the way back to our initial solution here. One last thing we can try. Because these gave us our best answer so far, let's go back to that. All right. This is my last attempt. Basically, all I did is add a new macro here. I'm calling them macros, they're not really macros, but made this variable here wrap none so we can have a nice clean looking code. And let's run this. What? That gave us our best performance so far. That, I am shocked. Now we're at a 97% for runtime and 72% for memory. What? How does changing a none to a variable make it go faster and improve our memory? That is crazy. All right, I can't really explain that one, but I'll take it. All right, well, that is it for me. I hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.